Welcome to the debate. Today, we are focusing on a single but really critical control knob in conditional generative AI, the guidance weight, omega. This parameter it sits right at the heart of Classifier-Free Guidance, CFG, which is the mechanism that really revolutionized diffusion models. It works by linearly combining conditional and unconditional score estimates to dramatically enhance the perceptual quality of generated images.
And it works incredibly well, which, is why this is such an interesting point to dig into. CFG fundamentally lifted the game for conditional generation quality. So the question isn't really if guidance works, but, have we actually pushed it as far as it can go?
Exactly. The core controversy here is whether that guidance weight should stay as a fixed static constant. Maybe, adjusted via a simple preset schedule like limited interval guidance or LIG, or if achieving truly state-of-the-art conditional sampling needs us to learn a dynamic guidance weight. We're talking about omega sub c, s, t, a weight that's a continuous function of the conditioning input c and the specific time steps s and t involved in the denoising process. So I'll be arguing that for superior distribution alignment and, frankly, better fidelity, this learned dynamic approach is essential.
And I'll be presenting the view that, the simplicity and the really robust empirical success we've seen with fixed or basic guidance methods already give us sufficient quality for most practical uses. We have to seriously question the, let's face it, significant complexity, the tricky optimization challenges, and the operational overhead that comes with trying to learn such a complex dynamic function.
Right. While, cranking up a constant guidance weight certainly makes an image look perceptually better. It gets crisper, more detailed. It's pretty well documented that this comes at the cost of distributional alignment. It tends to push samples toward the edge of the true data support, making them, less representative of the actual underlying data manifold. So to genuinely approximate the target conditional distribution, P of x0 given C, we really need to move beyond these static weights and learn them dynamically. Our method bases this learning in the kind of fundamental physics of the diffusion process itself. We minimize the distributional mismatch using a principled approach we call the self-consistency condition.
I see that maybe as searching for a level of precision that just might not be practically necessary. I mean, when CFG first came out, the justification was sort of rooted in sampling from a mathematically modified distribution, right? But then later work actually showed that standard CFG doesn't really sample from that specific theoretical distribution. It just kind of shifts samples towards the high-density areas, the modes, of the true distribution P of x0 given C. And it yields this huge quality boost while doing it.
Right.
So this suggests to me the goal maybe should be practical. High-quality results what the user actually sees, not necessarily perfect distributional alignment forced by, complicated mathematical consistency rules. And speaking of simpler methods, you mentioned limited interval guidance, LIG. That's a good example of effective simplicity, isn't it? LIG just applies guidance within a certain interval of the diffusion steps, showing that even a pretty basic scheduler can significantly impact quality without needing a whole new neural network just for optimization.
That's true. LIG offers some improvements, but it's still a bit of a blunt instrument, I'd argue. We believe the core problem we're trying to solve is really fundamental. Addressing the systematic mismatch between the samples you get from the guided process and the samples that should be generated by the true conditional diffusion process. We tackle this by minimizing rigorous distributional distance measures, like the generalized maximum mean discrepancy, or actually a much more computationally friendly proxy, a specialized L2 objective derived directly from our self-consistency condition. And, the empirical results really speak for themselves here. This approach gave us the best Fréchet Inception Distance, or FID, which is a metric strongly correlated with true distribution alignment, hitting 1.99 on ImageNet 64 by 64. That outperformed unguided models, constant CFG, and the LIG baselines. The lowest FID suggests we're getting samples that are both high quality and more faithful to the target data distribution.
That's an interesting point, though I might frame it a bit differently. Like, why does any guidance work in the first place? It's because the neural network doing the denoising, the x hat theta of XTC, is almost by definition an approximation. It's just not the perfect mathematical expectation, E of x0 given x, t, and c. So fixed CFG is really just an effective, simple correction mechanism. It compensates for the known imperfections of that underlying backbone denoiser. You even mentioned findings suggesting that if you could use a guided score matching loss to train the denoiser perfectly, the optimal guidance weight would actually go to 0.
Mm-hmm.
This implies the whole need for guidance is basically an error correction mechanism.
I absolutely agree that fixed CFG is an error correction, but the variability we see shows that the amount of imperfection changes drastically depending on the input on C. So a static correction is just fundamentally inadequate for what is actually a dynamic error. Our approach, minimizing that L2 objective, aims to reduce the distance between the mean of the guided sample and the true noised sample, while also minimizing the variance of the guided sample components. So we're directly optimizing the correction mechanism itself, making it adaptive. And the fact that the simpler L2 objective worked effectively and is much cheaper to compute than the full MMD approach suggests the computational framework is actually robust enough for practical implementation. It directly tackles these model approximation errors in a flexible way.
But doesn't this lead us straight back to the complexity baked into making the weight dependent on the conditioning? You have to train a whole separate network, omega phi, just to predict the best guidance strength at each point.
You absolutely do, yes. But the necessity, I think, is undeniable. We just cannot treat all conditioning signals the same way. Take ImageNet, for example, where the conditioning is just a simple class label. We looked at the learned guidance weights for different classes. For class 83, the prairie chicken, the learned guidance weight was actually near 0 across the whole timescale. This suggests the conditional model was already pretty good at generating that specific class, needing minimal help.
Okay.
But then for class 696, the paintbrush, the learned weights were much more aggressive positive over a larger time interval. This huge conditioning-specific difference proves that any constant guidance value, whether it's omega equals 4 or omega equals 7, is fundamentally limiting. For companies building, say, robust commercial text-to-image applications, using complex embeddings like CLIP and T5 on massive backbones, maybe like Flux, this variability could be the difference between a really high-fidelity output and just a poorly structured, low-quality image.
That is a compelling point about the variability across inputs, especially in that high-dimensional T2I space. But let's just pause on the optimization complexity for a second. You're optimizing omega not just based on C, but also across the time steps S and T. This feels like it introduces significant, maybe engineering fragility? The ablation study showed something really counterintuitive. Training the guidance network actually performed better when using a large step gap, like delta around 0.1, between time steps S and T.
That's right, yeah. A larger training gap did provide stability during training.
Okay, but during actual inference, we typically use very small gaps. Maybe ST is around 0.01 for, say, 100 total diffusion steps. So this means that the complex learned network, your omega phi depending on C, S, and T, is being forced to generalize massively from a sparse training setup, those large steps, to a very dense inference setup with small steps. Aren't we relying entirely on the sort of architectural smoothness of this new guidance network to make a pretty huge leap? That feels fundamentally fragile for production systems where, robustness and stability are absolutely paramount. The marginal gains you see in FID might come at the cost to just ease of deployment.
I'm not fully convinced that the generalization jump necessarily means fragility. It could also be seen as a demonstration of the neural network's ability to actually model the underlying smooth dynamics of the score function correction. And it's worth remembering, when we initially tried to optimize these guidance weights using a different approach, the marginal consistency objective, we actually found it was impractical. It suffered from prohibitively high variance.
Ah, that's a crucial detail. What does high variance mean there in practical terms? Like, what happens?
It means that if you tried to train the network using that particular objective, the optimization landscape was just way too rugged. The gradient estimates were bouncing around wildly, making it basically impossible for the model to converge reliably to any meaningful solution. This is what forced us towards computationally simpler, lower variance proxies, like the L2 self-consistency objective we ended up using. So this whole line of research is, in a way, a sophisticated effort to find a stable method to correct what is inherently an unstable error source. If we can achieve stability and better alignment through this learned method, even with the architectural overhead, I think the payoff in model fidelity is worth it, especially when you think about fine-tuning models later on.
Right, which brings us back to practical application. So if we accept the complexity for a moment, where does this learned guidance truly give a critical edge beyond just slightly lower FID scores?
Well, the real power of learning this dynamic weight, I think, reveals itself when we move beyond simple internal metrics like FID and start optimizing for something the user actually cares about, like prompt alignment and text-to-image systems. We extended this framework to what we call reward guidance sampling. This lets the model target distributions that are tilted by some arbitrary reward function R of X0C. We use this on the MS COCO dataset, leveraging the clip score itself as a reward function. This ability to learn guidance weights that actually optimize against user-relevant metrics is, I think, a critical practical advantage over static CFG. Figure 3 in the paper visually showed that the learned guidance weights were highly variable and very prompt-dependent when trained with this clip reward. It demonstrates an adaptability that constant CFG just fundamentally can't match. This allows us, potentially, to fine-tune the model much more precisely to the specific aesthetic or semantic needs of a product.
I see why you'd emphasize that capability, sure, but let me give you maybe a slightly different perspective on the quantitative reality in that T2I application. Even when you incorporated the clip score reward, the quantitative results showed that the learned guidance achieved a clip score, the measure of image prompt alignment, that was quantitatively basically identical to the guided baseline, which just used a manually selected constant omega of 7.5.
But the FID was substantially lower. We got the same subjective alignment, essentially, but with much better distributional properties.
Okay, but the critical metric maybe for user quality, the prompt alignment itself, wasn't overwhelmingly superior in score. And furthermore, your method needed pretty robust regularization. You had to stabilize the reward loss using the self-consistency loss. Doesn't that suggest that simply minimizing the reward function directly led to that well-known generative AI problem of reward hacking?
That's actually correct, yes. If you just minimize the reward loss alone, the model absolutely figures out the quickest and often artifact-filled path to maximize the clip score without necessarily generating a coherent, high-quality image. So the distributional self-consistency loss is essential. It enforces that the guided distribution stays, reasonably close to the true conditional distribution while also maximizing the reward. This integration, I think, proves that the complex distributional mechanism isn't just complexity for complexity's sake. It's the necessary foundation for effectively leveraging these user-centric metrics without, catastrophic failures. Or
Well, ultimately, learning the guidance weights omega sub c st through self-consistency provides, I believe, a robust and principled method for achieving demonstrably better distributional alignment. This is evidenced by consistently lower FID scores across major benchmarks and the highly variable nature of the optimal weights depending on the conditioning signal and the time step, as we saw when comparing different ImageNet classes or complex text prompts, demonstrates pretty conclusively, I think, that constant guidance is fundamentally a suboptimal simplification when you're really seeking maximum fidelity.
Look, I still think standard CFG is the workhorse here, or perhaps simple schedulers like LIG offer a good balance. While learning dynamic guidance does offer those, yes, marginal FID improvements, the intense complexity of its training objective, the reliance on generalizing from large training steps to small inference steps, and, importantly, the quantitative similarity to simple guidance in crucial user-facing metrics like clip score alignment, it all suggests it remains a high-cost solution for maybe limited practical gain in many scenarios. Simplicity and robust empirical quality, at the end of the day, will likely always be primary drivers for scaling real-world generative applications.
The findings definitely illuminate that optimal guidance isn't just a fixed number, but a highly dynamic variable. It's defined by the input and the stage of generation. And this really suggests that future research has to thoroughly investigate how these time and conditioning dependent guidance weights fundamentally affect the sample distributions. That's how we'll bridge the gap between just perceptual quality and true distributional accuracy, moving us, hopefully, closer to genuinely intelligent generative systems.